computer. So let me record this meeting. Uh, yeah. So we have already talked about a short review on the difference between sample mean and estimation. So you can like look through the lecture notes if you are watching the webcast. And then we went through problem 1A, and we are currently in problem 1B. And want to do a Z-score transformation on the probability we have here. So a Z-score transformation is, we know that the variable, what happens on the variable is a minus mu bar divided by sigma bar. So on the left and right hand side, it's mu minus 10 minus mu bar divided by sigma bar. And on the left hand, the right hand side, mu minus plus 10 minus sigma bar over minus mu. So we know that mu and mu bar are the same. So at the end of the day, it will be just negative 10 divided by the sigma bar, less than z less than 10 divided by sigma bar. And we know that sigma is 5.37. We calculate in part A. And then we just plug in here. The answer is about negative 1.86, positive 1.86. And if we check the normal table for z of 1.86, that's approximately 0.4686. Because we are doing like because it is symmetric, we need to like time it by 2. So the answer is 0.9372. And for part C, that's where the estimator comes in, because we are giving a specific sample. So this specific sample has each individual has a specific number. That's our sample. And for a specific sample, we need to use estimator. Like we call that estimator for mu is just calculating x bar, which is x1 plus x5 divided by 5. Like this x bar is like different from the random variable x bar. It's just like the way they calculate is the same. It's just like getting the mean. Like, but this mean is not like for random variable. It's for like concrete numbers. So the concrete number is 110 plus 100 plus I don't want to write it, divided by 5, and the answer is 108.6. And the standard deviation estimator is defined to be n minus 1 over 1 summation from k from 1 to n at k minus x bar squared. So in this question, n is equal to 5. So we plug in 5. 5 minus 1 square root k from 1 to 5 at k minus and what is x bar? X bar is what we just calculate is 108.6 minus 108.6 square, and like we just plug in these 5 numbers as sk, and then calculate the result, and the result will be around 7.403. And then confidence interval. Oh, I realized I forgot to review confidence interval. So confidence interval is something, it's defined to be the interval that we are 95%, like we are like somehow however percent confident that we will have mean, we will like include the mean. So the saying that this is 95% chance that mean will lie in this interval is false, because the mean itself is fixed. It's not a random variable. So we can't say that mean lands, the probability of mean lands in some interval. Instead, we should say like after calculating the interval, we have 95% chance or confidence that we will have mean in our interval. So it's like kind of like interval itself are shifting instead of mean shifting. So this is something you need to know. And usually like we're dealing with 95% confidence interval because like in statistics, this is the interval that we are like fairly confident to draw results So like usually for any like experiment, we want to check if it passes the 95 interval test, make sure that it's good enough. So the 95% confidence interval is mu minus 2 sigma divided by n, mu plus 2 sigma divided by square root of n. And this 2 comes from the z-score of like z-score corresponded to like 95% over 2. So I believe that's like z-score of, so I believe 2 is the z-score of 0.475. Yes, so the confidence interval for other things could be pretty much different. So for 90% confidence interval, we are dealing with the z-score of 0.45, and it is equal to 0.1645. So the 90% confidence interval becomes mu minus 0.1645 times sigma divided by square root of n, mu plus 0.1645 divided by the square root of n. Yeah, I mean, and you can do like your own confidence interval. Like you just calculate the percentage of p and divide it by 2 and find the z-score for that, and use like this constant as this constant here, and you will find your own confidence interval. Okay, so that's pretty much a review on confidence interval. Let's go back to this problem. This problem says we want to find the confidence interval, 95% confidence interval for this sample. And since we have already had the value of mu bar equal to 108.6, sigma bar equal to 7.403, we just plug into the confidence interval formula to get the confidence interval, and it's 5 in this case. So at last, the answer is what I've shown here. You can also like test it by yourself. So we know that the actual population mean is 110, and it fails our if and our like interval successfully catch that mean. So like very good. So that's a lot for problem 1. Now take your time to work on problem 2 and problem 3. And feel free to ask me any question if you have. Yeah, and please update your progress with me, so I know like how long do I need to wait. Okay, some of students finished problem 2, so now work on problem 3. And for those who haven't finished problem 2, also work on problem 2, please. And also you can ask me any questions. Okay, I'll probably walk you through problem 2, and then you can have more time on solving problem 3. Or actually, I'll go through 2 and 3. Most of you has already finished 2 and 3. No, most of you already finished 2 and some of you finished 3. So for problem 2, we make a so Maya shots basketball 100 times and make 3 shots. So we know that the 95% interval, we're finding the 95% confidence level. The confidence level is given by this formula. But we don't know like information about this random variable now. So we need to calculate by ourselves. So we know that there's 73 shots. So that means the proportion of success is 73 over 100. And this random variable is a Bernoulli random variable with a success rate of 73 over 100. And the way we calculate the variance for a Bernoulli random variable, screen frozen again. Stop share. Okay, so the way we calculate the variance for a Bernoulli random variable is P times Q, which is the success times the failure. In this case, the answer is around 0.444. And we know that n is equal to 100, and we know that the sample the like estimator from mean is 0.73. So we can plug this number and calculate the confidence interval. And for part B, we want to estimate the variance of curve making a shot using the estimator of variance. So again, like since this is a Bernoulli variable, it only has 1 and 0 for each shot. It can be either success or failure. So but we know that the proportion of the x bar itself is 0.73 that was given. So x squared is n minus 1 over the summation from 1 to n xk minus x bar squared. This is equal to 100 minus 1 over 1. And what is in the summation? Like in the summation, we know that 73 of them are success. So 73 of them xk equal to 1 because it's a Bernoulli random variable. And 27 of them are failure. So 27 of them xk is equal to 0. So we have like 1 minus x bar, or x bar is 0.73. So 1 minus 73 squared plus 1 minus 0.7 squared plus a lot of them. In fact, there are 73 of them here. And plus 0 minus 0.73 squared plus 0 minus 0.7 squared here. And we have 27 of these terms. So in fact, the answer is 100 minus 1 times 73 times 1 minus 0.73 squared plus 27 times 0 minus 0.73 squared. And if you calculate that, that's around 0.199. Yeah, and I believe on the midterm, you are not allowed to use a calculator. So if that's the case, you can just leave the answer here. If your calculator is odd, like we will know that you use a calculator. Like most likely. And for problem 3, we're given a specific sample here. And this sample, we already tell you that this is a Poisson random variable. And in fact, if you don't know it already, a Poisson random variable is usually a measurement of at a specific so it's like a number of people. For example, it can be like a number of people going through Sager gate in a specific time period. It can also be like a measurement of like given a specific time and given a specific area, like how many raindrops fell on the ground. So if you don't know that already, Poisson variable is a measurement of that. But like if you recall previously, a Poisson random variable is mean. It's like a standard deviation. Its variance is just the parameters lambda input. So the standard deviation is just square root of lambda, which is also provided here. And we know that lambda hat here is x bar. That was also given. So the first problem, we want to calculate the 95% confidence interval. So I'm just like rewriting the formula for 95% confidence interval again. This is I don't know if is that in the scope? No, it's not in the scope of meter 2, but like this will definitely show up on the final. So we look at the equation. What information do we need? We need lambda bar, also need sigma bar. So lambda bar is x bar. It's just like summing through all this information here. So 11, I believe there's 10 information. So 11 plus 5 plus 3 plus them together divided by n. That's our like estimator for the mean, which is 5.6. And the estimator of sigma is just the square root of 5.6, which is about 2.37. So we just plug in 5.6 here and 2.37 here, and we'll get our result. And for part B, we are estimating the variance using the formula provided. So again, we just plug in the formula. It's just one, so maybe I should rewrite the formula in case you forgot. So that's the formula for unbiased estimator for variance. We plug in number here, and it's 10. Okay, it's from 1 to 10. And each SK is a data point of our sample. We have 10 data points here. So 11 is our first data point, minus 5.6 squared plus 5 is our second data point, plus 9 is our last data point. So calculate the results, that's about 8.044. And maybe I should go through problem 4 as well. So problem 4 is a very simple question. The problem asks you the age of onset of multiple, whatever, I don't know this word, polynomial variables and no mean and standard deviation. So this question, we don't know the mean, but we have a standard deviation. And we want to calculate the probability that the sample mean falls within 2 years of the true population mean. So the thing we want to calculate is for the random variable x, a length in -2 and +2 of the mean of the true population mean, but we don't know this population mean. But what we know is that if we do a transformation to this score, we can cancel this mean off. So that's just this value minus mean. Let me write the variable first. We're doing we're doing a transformation like that. We know that population mean and sample mean are the same, so we can cancel this off. And what is the sample standard deviation? It's just the population standard deviation divided by square root of n. The population standard deviation is given by 7.6, and n is given by 32. So the result is 1.34. So again, like we just plug in number, -2 over 1.34, +2, 1.34. And the answer is -1.79, +1.79. So if you look at the z-score table for 1.49, that's about 0.4319. So this probability is just 2 times, because this is symmetric for -2 to 0 and from 0 to 1.49. So it's about 2 times the z-score of 1.49, 0.4319. The answer is 0.868. So let me know if you have any question in the first section. And I'm doing a short poll here to take the attendance. Let me see, polling lunch poll. Okay, you guys should be able to access that pool here. You have 2 minutes to do the pool. Okay, you have 30 seconds left to do the poll. If you didn't do it in 30 seconds, it will be counted as absence. Okay, 15 seconds left. Okay, whoever didn't do that, do it now, and I will close in precisely 3 seconds. 3, 2, 1. Close pool. Okay. So let's see. The first problem, we use estimator when there is a specific statistic. Yeah, that is correct, and that is exactly what I want to emphasize. Yeah, yeah. So like, remember, like for previous problem, when we have like 10 data points, that's when we have a specific statistic. So we use estimator to calculate the parameters and calculate the confidence interval. So it tells us like how well like our confidence interval is includes the meal, the population mean. The second question is false. So if I construct a 95% confidence interval, then I can say that probability is that mu length in interval is 95%. That's very false. That's exactly what professor mentioned in the lecture, that because mu is fixed, like mu can be changed. We can't say that mu has a probability length in an interval. Instead, we are saying that the interval itself are shaping to fit the fixed mu. So like if we do like a lot of confidence interval, there's like if we do 100 interval, there is expecting 95 of this interval that will include mu. So definitely be sure about be aware of this definition. It will maybe reappear sometime in the future. So yeah, so let's move on to section 2, midterm review, and work on problem 1 and 2 by yourself. And I will give you about 6 minutes or 7 minutes on doing problem 1 and 2. Please update with me your progress on solving this problem. Okay, I just finished grading your question, and it should be up on your Gradescope right now. So we are doing like very well on this quiz. And actually I make it pretty like easier than usual. So it's like I hope you can have like very confident feeling before like going to midterm 2. So but like also like you just like need to be very confident, and you should be very confident. So the like a lot of you get like very good score. A median on a 14 scale is 13. So let's talk about like statistics of quiz. So the median on the 14 scale is 13. And the mean is 11.79, and the SD is 3.17. So like so that's on 14 scale. So on the 12-point scale, a median will be 11. A mean will be 9.79. So yeah, we're doing pretty good. Yeah. So yeah, just congratulations on you doing pretty well, and like go back to like working on your discussion problem and update with your current progress with me. Okay. Okay. So most of you, like a lot of you, have updated with me on your current progress. Yeah. And actually, no one has any questions to ask me. So I'll probably just go through the solution right now. So for problem 1, that's what we do it a lot of times recently. So in order for a function to be a valid PDF, it has the summation, like the integral for the continuous variable from negative infinity to positive infinity has to be 1. In this case, as at part A, only -1 to 1 is what we concern, because every place where else are 0. So we just need to check if from -1 to 1, this integral results in 1. So we solve this integral by just solving it from -1 to 1, and we solve this equation, and we get the constant of 3/4. I'm kind of like skipping a lot of steps, but you should be able to do the integral calculation by yourself. And the second question, again, like, but the interval, like the range of x that is non-zero was changed to 10 to positive infinity. That's where like x is non-zero. and we plug this function in and want to solve this equation. And then we just calculate the integral that's negative c over x from 10 to plus infinity equals to 1, and we get c is equal to 10. And for part C, this is a little bit trickier. It includes like two variables. So fx is a plus b squared, and x is zero, like when like only 0 to 1 is what we concern when x is non-zero. So we kind of need to like write out two equations. The first one is we are given the expectation of x is 3 over 5. And we know that the way we calculate the expectation is integral from 0 to 1, specifically for this problem, x fx dx, which in this case is 0 to 1 x times a plus bx squared dx, which is from 0 to 1. And if you calculate the integral, that's a over 2 plus b over 4. And we are given that this is the expectation, and this value is equal to 3 over 5. And another information we can gain is that since it's a valid probability density distribution, we know that on the range where x is non-zero, it's equal to 1. So if we solve the integral of ax plus bx cubed over 3 from 0 to 1, which is a plus b over 3, it's equal to 1. So we have first equation, second equation, two equations and two unknowns. So we can solve a and b. A is equal to 3 over 5 and b is equal to 6 over 5. That's the solution. And for problem 2, so problem 2 is discrete variable problem probability distribution. So looking at the problem, we want to like draw 10 tickets out of 50 tickets, and part A, we want A exactly to be 4 red tickets. So after reading the problem, we notice that this is a hypergeometric distribution. Why is it a hypergeometric distribution? Because we know that how many in total the tickets we have, and we have some of the good tickets and some of the bad tickets. We want to get something from the good tickets because we're already know that we need to get 10 tickets out, and some of them are from the good tickets, and some of them are from the bad tickets. And that's why we know that this is a hypergeometric distribution. And how do we calculate the probability that x equal to 4? That's just when, like in total, if we don't care about good or bad, we need to take 10 out of 50. But now we do care about good and bad. We want to take 4 good tickets with 4 red tickets. And red tickets we have 20, so we take 4 out of 20. But in the meantime, we are taking 10 tickets out. That means we need to take 6 bad tickets out of 30 tickets, and that's precisely the result of Px equal to 4. But like again, like why is it hypergeometric distribution? It's also because it is draw without replacement. So like each time the probability is different. But if we draw with replacement, that means after one draw, the second draw has the same probability as the first draw. So that's the binomial distribution. So we know that we're doing 10 Bernoulli draws, and each of them has 0.4 probability of success because we have 20. We call like drawing a red ticket as a success. So we have 20 tickets out of 50. So that's 0.4 success rate. And the probability of x equal to 4 for binomial distribution is just 10 to 4 times the success rate. We have like 4 success rates and 6 failure rates, and that's just the solution. And this is with replacement. Okay. So now I want to skip problem 3 because that's too easy. It's just know Poisson distribution, the distribution for probability distribution for Poisson distribution and plug in numbers. So let's work on problem 4. That's about Bayes' theorem, and I believe a lot of you may have already forget how to do that. Work on problem 4 now. Let me know your progress on solving these problems. Yeah. Oh, and by the way, I'm like looking through your degree request. Sylvia, I believe you didn't like put it on Google Drive. You just like copy and paste the text on your desktop, so I can access your quiz correction. Okay, so let's go through problem 4. Remember like what I told you in discussion. How do you calculate? How do you do this problem? Is to like an easier way is to draw a tree diagram. So you first identify which event happened first and which event happened second. So for this problem, let's say event A is the number of the proportion of population that actually use opium. And event B is the test, how accurate the test gave you the result. Because we need to like have the person who use opium first and then do the test. So that's the order. So we know that 0.01 of the proportion use it, and the other doesn't use that. And the test gives a 0.05 when it is incorrect. That means like it actually used the opium but doesn't test it out. Yeah, 0.05. And then there are like 0.02 people who didn't use the opium test but test positive, so that means the test is inaccurate. And then we can like do the complements and calculate the results. So maybe like let's work on part B first. So part B, we're asked that when the probability someone who tests positive for opium actually use the opium. So again, that's like we define A as using opium and we define B as test positive. Test positive. Yes. And in fact, I think like inaccurate is not a good word here because we are doing it is positive or not. So if it use, it's supposed to be positive. And it doesn't use, it's supposed to be negative. So that is more better for a tree diagram. So for B, we want to calculate the probability that test actually use opium given that it tests positive. So that's just P A given B. That's what we define for the event. And according to Bayes' theorem, what is P A given B? That's P B given A times P A over P B given A times P A plus P B given A complement times P A. So we know that P B given A is when like it actually used opium, but and it tests positive, yes. So that's 0.95 times 0.01. That's the same thing here. Plus PB given A complement. A complement is not used, so not used here. And B is test positive, so it's 0.02 times P. It should be A complement here. Not used 0.99. So that's the result. And it's actually equal to 0.3242. And then let's go back to part A. Part A, you want to find the probability that someone who tests negative for opium that does not use the opium. So we want to find the population who does not use opium, given that it tests negative. So test negative is B bar because we define B as test positive, and not used is A bar because we define A as used. So we can write in Bayes' theorem. So that's like the standard format for Bayes' theorem. We just plug in A bar and B bar in this formula. So that's P of B bar given A bar times P of A bar over P of B bar given A bar times A bar plus P of B bar given A times P of A. So what are these numbers? A bar is has negative, so that's A bar is not use opium, 0.01. Well, no, like 0.99. Sorry about that. And B bar given A bar is not use opium. Given not use opium has negative, so that's 0.98. So on denominator is 0.98 times 0.99 here. And what is PA? PA is actually use opium, so this 0.01. And what is P bar given A? So given A is using the opium, and B bar is test negative, so it's 0.05 our tree diagram. So that's the result, and the answer of that is 0.9995. Okay, great, we are right on time. So that's the end of the section. So I will wait for 1 extra minute to answer a quick question. Otherwise, you're free to go. You're dismissed. Where can we download the PDF for the midterm 2 format? I don't know. Like you do midterm 2 on WebWork, right? Or the PDF for the midterm 2 format. I have no idea what you're asking. Please clarify your question. For part 2, she says we need to label the question a certain way so we can submit it on Gradescope. Yeah, then you just do the labeling on Gradescope, right? I know what you're asking. So like if you just submit on Gradescope, you just do the labeling as you did on my section on submission on quiz. If there's like a further question, maybe like ask on Piazza, where like every like professor and other GSI and other student can answer this question. Can you do 14 nanometer review package? Oh, okay. That's actually exactly what a student asked me during my office hour. Yeah, I guess I can just do it for you right now. So the problem I remember is for like X, Y are picks out of 10. Yeah. So like X is the first pick, and there are like 6 success, I believe. So X is like a Bernoulli variable of 10 over 6. And Y is also a Bernoulli variable of 6 over 10. Because like you can treat X, Y as like indicator. Another way of doing that is like you can say like if X is success, if success, Y success is 9 over 5. 9 over 5, yeah. If it fails, it's like 9 over 4. And this is success in 9 over 6. If It fails is 9 over okay, let me stop share, reshare. Yeah, that's what I wrote here. So if a success, that's x, that's y. If x success, what will happen? If x fail, what will happen? So if you want to calculate success for y, that's just 10 over 6 times 9 over 5 plus 10 over 4 times 9 over 6. So that's also like 6 over 10. So we know that x and y are two Bernoulli variables with 6 over 10. And you want to find the covariance between x and y. That's just the expectation of x, y minus the expectation of x times the expectation of y. So since they are all Bernoulli variables, so x times y equals to 1 only when x equals to 1 and y equals to 1. It will be like 0 otherwise. So so the way you do that is you calculate the probability that x, y are both 1. So x, y are both success, I think. Maybe I should go to the previous problem right here. No, it's not. Oh, it's actually this one. Kind of forget what I did here. So yeah, that's exactly what I did. So why is it now we're 30 again? Oh yeah. So expectation of x, y is just when x is success and y is also success. That's what I mentioned on the previous page. So it's just 10 over 6 times 9 over 5, which is 90 over 30, which is the number here. And expectation of x and y, since they are Bernoulli variable, is just their probability. So the covariance is this minus this, and that's just negative 2 over 75. Yeah. Are you good with the solution I provided? Yeah. Yeah. And I will see you. Like I will end the meeting now.